In this part 3 of lecture 2, we investigate integral and rational points on some particular hyperbolas. We start our study with the famous hyperbola of equation x squared minus 2y squared equals 1. This equation is a particular form of a more general equation, the so-called Pell equation x squared minus ny squared equals 1. The Greeks studied the special case x squared minus 2y squared equals 1 because they realized that the natural number solutions of this equation throw light on the nature of square root of 2. Now, before we investigate integral and rational points on the hyperbola, we shall make the connection between this equation and the nature of square root of 2 a little bit more obvious. Indeed, it is very easy to find the decimal expansion of any fraction of the form x over y by using the high school division algorithm. For instance, on the one hand, if you'd like to divide 3 by 7, we first get a 0 here, we get a remainder equals to 0, 3, we add a 0 to find 4, 28 as a remainder, we get a 2 here, 20 divided by 7 is a 2, and so on and so forth. Actually, we get the decimal expansion of 3 over 7 very easily with the remainder division algorithm. On the other hand, it is not very obvious how to compute the decimal expansion of square root of 2, but we will see that surprisingly, the natural solutions of x squared minus 2y squared equals 1 give the decimal expansion of square root of 2. More concretely, if xy is a natural solution of x squared minus 2y squared equals 1, and if we suppose that y is different from 0, then by dividing by y squared both sides of the equation, one gets x over y all squared minus 2 is equal to 1 divided by y squared. Now if y is big enough, this means that 1 divided by y squared is almost 0, which means that x over y is almost square root of 2. This fact is actually very exciting because now, in order to compute the decimal expansion of square root of 2, all we have to do is to find the natural solutions to the equation x squared minus 2y squared equals 1, and we will see that this is actually very easy. Notice, for instance, that the couple 17, 12 is a natural solution to our famous equation because 17 squared minus 2 times 12 squared is equal to 289 minus 288, and which is equal to 1. And if one computes 17 divided by 12 by our division algorithm, one gets 1.41666 and so on and so forth. And we can notice here that this fraction shares the 3 first decimals of square root of 2. Now, in order to find better approximations of square root of 2, one has to get bigger solutions of our equation x squared minus 2y squared equals 1. Indeed, first notice that the couples plus or minus 1, 0 are both trivial solutions to the equation x squared minus 2y squared equals 1. By trial, one notices that the first non-trivial couple solution to our equation is 3, 2, and we can check this because 3 squared minus 2 times 2 squared is actually equal to 1. Now, before I show you how to compute all the other integral solutions to our equation, go take a deep breath because this is really fantastic and breathtaking. Indeed, if you square the number 3 plus 2 square root of 2, one gets 3 squared plus 2 square root of 2 all squared plus 2 times 3 times 2 square root of 2. And after straight calculations, we get 9 plus 8 plus 12 square root of 2, which gives us 17 plus 12 square root of 2. Surprise! As we have seen before, 1712 is actually a solution to our equation. Now, if we do the exact same thing with power 3, one gets 3 plus 2 square root of 2, all cubed, is equal to 3 plus 2 square root of 2 squared times 3 plus 2 square root of 2. We then get 17 plus 12 square root of 2 times 3 plus 2 square root of 2, and after straight calculations, one gets 99 plus 70 square root of 2. And one can check easily that 99 squared minus 2 times 70 squared is actually equal to 1. Whoa, this is actually really incredible. Now the first good question is, do we get all the integral solutions to our equation in this fashion? The answer is yes, but the proof is slightly complicated. The second good question is, how does this work actually? Why do we get integral solutions in this fashion? Indeed, if x1, y1 is a solution to our equation and x2, y2 is another solution of our equation, we know that x1 squared minus 2 y1 squared is equal to 1, and x2 squared minus 2 y2 squared is also equal to 1. This first equality here implies that x1 minus y1 square root of 2 multiplied by x1 plus y1 square root of 2 is actually equal to 1. And this second one here implies exactly the same thing, that x2 minus y2 square root of 2 multiplied by x2 plus y2 square root of 2 is also equal to 1. Now if we subtly multiply both of these equations, one gets x1 minus y1 square root of 2 times x2 minus y2 square root of 2 times x1 plus y1 square root of 2 times x2 plus y2 square root of 2 is equal to 1. 1 times 1, which is equal to 1 actually. Now if you multiply the first two terms, one gets x1, x2 plus 2y1, y2 minus x1, y2 plus x2, y1 square root of 2. All times both of these terms, we get quite the same thing actually, x1, x2 plus 2y1, y2 plus x1, y2 plus x2, y1 square root of 2 equals to 1. I know that you're probably lost here, but notice that we got something of the form a minus b square root of 2 times a plus b square root of 2, and this is actually equal to a squared minus 2b squared. So we get here x1, x2 plus 2y1, y2 all squared minus 2 x1, y1, y2 plus x2, y1 all squared equals to 1. Let me write this down one more time. Actually, the formula is x1, x2 plus 2y1, y2 all squared minus 2 times x1, y2 plus x2, y1 all squared is equal to 1. This is actually incredible because it means that the new couple x1, x2 plus 2y1, y2, x1, y2 plus x2, y1 is a new couple solution to our equation derived from both of the couples x1, y1, x2, y2. Said in other terms, if x1, y1 and x2, y2 are both solutions to our equation, then by multiplying x1 plus y1 square root of 2 times x2 plus y2 square root of 2, one gets actually a new solution. And this is actually what happened with 3 plus 2 square root of 2 all squared, because all we've done here was multiplying 3 plus 2 square root of 2 by itself. And this gave us a new solution to our equation. So to conclude, all the integral points on our hyperbola are encoded in powers of 3 plus 2 square root of 2. And we've seen that the first one was 3 plus 2 square root of 2. The second one was 3 plus 2 square root of 2 all squared, which gave us 17 plus 12 square root of 2. And the third one was 3 plus 2 square root of 2 all cubed, which gave us 99 plus 70 square root of 2, and so on and so forth. Now we move on and try to locate all rational points on our famous hyperbola. All we have to do is to apply Diophant's-Codd method, which we've seen in Lecture 2, Part 2. To do so, notice first that minus 1, 0 is an obvious rational point on our hyperbola. And in order to find all the rational points lying on our hyperbola, all we have to do is to trace lines with rational slopes passing through A, and we know from Diophant's that the second points of intersection are all rationals. Indeed, if L is a line of rational slope t passing through our point A, then it has equation y equals t times x plus 1. So in order to find the coordinates of the second points of intersection of our line L with a hyperbola, one has to solve the system of equations x squared minus 2y squared equals 1 and y equals t times x plus 1. By substituting the first equation into the second, one easily finds that x is 1 plus 2t squared divided by 1 minus 2t squared, and y is equal to 2t divided by 1 minus 2t squared. Notice here that 1 minus 2t squared is non-zero because t is rational. Hence, all rational points on our hyperbola are of this form, and if we take, for instance, t equals to 0, one finds x equals to 1 and y equals to 0, which is our point here, 1, 0, which is obvious as well. We will study hyperbolas in depth in future lectures, but before we do so, one good question is, does every hyperbola have integral points on it? The answer to this question is no, as we shall see in the following example. If xy is an integral point on our hyperbola, then we must have x squared minus 5y squared equals 2, which is equivalent to x squared equals 2 plus 5y squared. This means that if we divide x squared by 5, we get a remainder equals to 2, and we will see that this is actually impossible. In other terms, you must have x squared congruent to 2 modulo 5. If you do not know congruences, do not worry, we will get back to this in future lectures. But we know that either x is congruent to 0 modulo 5, in which case x squared is also 0 modulo 5, or x is congruent to 1 modulo 5, in which case x squared is also congruent to 1 squared, which is 1 modulo 5, or x is congruent to 2 modulo 5, in which case x squared is 4 modulo 5, and which is different from 2 modulo 5, or x is congruent to 3 modulo 5, in which case x squared is 9, which is also 4 modulo 5, and last, x is congruent to 4 modulo 5, in which case x squared is congruent to 16, which is 1 modulo 5. In all cases, we see that x squared is never congruent to 2 modulo 5, which means that this equation cannot have integral solutions. Lecture 2 part 3 ends here, and we will investigate in part 4 elliptic curves, which are central in cryptography. Thank you for listening.